Our next speaker is Pratik Jain. Pratik heads the foundations and optimizations team at Google AI. And Pratik has been working in theory of machine learning, non-convex optimization, alternating minimization, theory of deep learning. So he's very well regarded in all of these areas. Today he'll talk about reverse experience replay, effective way to learn with
All right. Thanks, Amit, for the wonderful introduction, and thank you everyone for attending the talk. Thanks to the organizers for this wonderful workshop. For this, I prompted GPT to produce this nice poem, where I would definitely want to sort of thank my collaborators Dheeraj and Praneeth, who have been main driver behind this project. But there are some other wonderful collaborators also who have contributed to this project. The goal of this work is to learn with dependent data. So before going into what we mean by that, let's first set up the problem, right? So suppose we want to do our standard machine learning, that is supervised in the supervised setting. That is, we want to minimize some loss function of a network or a model that is parameterized by this parameter W. And this loss function is measuring fidelity for a given data point X. And we assume that these data point X are sampled IID from some fixed distribution pi. Right. So here, stochastic gradient descent and algorithms similar to stochastic gradient descent are workhorse of such stochastic optimization. What they do is, at each step, they will sample one of the data points uniformly at random from this distribution, take the existing parameter WT, compute the gradient, and subtract it from the current parameter with some learning rate or step size, and this works well, right? And the reason this works well is that this is essentially, in expectation, just gradient descent, which means that, let's say, if the function is strongly convex, then we will converge pretty close to the optimal solution, at least in the function's value, up to an error of 1 by capital T, where capital T is the number of points that we have seen so far. Right? And this is known to be information theoretic in this setting. People have studied this optimization in variety of other settings. So, for example, when the function is not strongly convex, but it is smooth, or in some cases, people have also studied this kind of problem when the function is non-convex, when the function has some kind of min-max form. So the problem is very well studied in general, right? So this is a story for standard supervised learning. But in ML, there are various other paradigms which are quite interesting as well. So for example, you might have some kind of time series forecasting or reinforcement learning, where this nice assumption that all my data points are sampled IID from a fixed distribution might not hold. So let's look at time series prediction. So suppose this is some kind of, let's say, price graph of your stock, say stocks of Google, right? So you might, typically these time series are modeled with autoregressive models. That is, you will look at, let's say, the stock price value of 2 days back, yesterday, and then you will try to predict what is the price value today. Right? And like once you observe today's price value, you can say that, okay, this is my learning tuple. I will take xt minus 2, xt minus 1, and xt. Xt is my target, the value that I want to predict, and xt minus 2 and xt minus 1 are my inputs. And I want to come up with a network that is able to predict xt. Now, the next point that you will provide to your model to learn will be yesterday's value, today's value, and you will try to predict what is the value going to be tomorrow. And then once you observe tomorrow's value, you will again feed it into your system to update your parameters, right? So now these two tuples of points you can see are dependent on each other. So you cannot directly apply your standard SGD kind of analysis. Even more interesting problem setting happens in reinforcement learning. So in reinforcement learning, typically you have some kind of system. Let's say consider a board game. You have some kind of current state of the board game. You as an agent take some action. So you make some move on the board. And for that, you will maybe receive some reward, or you will go closer to your goal, right? So the tuple from which you would want to learn is some state, some action that you took, and some reward you obtained. Right? Now, once you have obtained that reward, you will then you will go into next state, right? So typically, based on the current state and the action that you've taken, you will go to the next state of the board, and that transition might be deterministic. In some cases, it might be probabilistic, but nonetheless, the transition will be dependent on the current state and the current action, right? And then in the next state, you will again take a new action to go to get some reward, and you will again try to learn from this tuple. And here again, you can see that there is intrinsic dependency between these sequence of points that you're getting. So this is what we are calling learning with dependent data. In general, you can model these dependencies between data points in a variety of ways. Let's consider very, very simple setting, which is quite applicable in practice also, which is that of Markovian chain. That is, we are assuming that these data points are sampled from some Markov chain. Right? And the goal is to design streaming SGD style algorithms for this Markovian data.
Yeah, and I think it's interesting to figure out whether these degree.
All right, so let's define the problem formally. Suppose I have a bunch of points x1 to xt. Coming from a Markov chain with some stationary distribution pi, and our goal is to optimize the loss function under this stationary distribution. Now, if you do standard SGD, that is at th step, you sample some data point xt and apply the gradient descent step to it, the standard SGD analysis does not apply anymore. And the reason is because xt itself is dependent on wt minus 1. So the expected value does not match the true gradient, right? So SGD will be biased, and in general, it might not converge to the optimal solution. You can try to get away from this problem by saying that, okay, I will do very, very small steps. But in that case, your convergence is quite suboptimal, so it's not desirable. And in practice, people generally don't do that.
You want to get as close to that as possible?
So how do we solve this problem? So there is one very simple idea, which is that because we are sampling from, say, some Markov chain, we are assuming that Markov chain has some finite mixing time. So mixing time, what it essentially means is that if you consider points which are the mixing time tau mix apart, then they are roughly independent of each other. So now what you can do is you can come up with a very simple baseline called stochastic gradient descent with data drop, where you take, say, point x0, you drop the next tau mix points, you take the next point, you do SGD with it. Because this x tau mix is almost independent of x0, you can apply your standard SGD analysis and get your good properties. You can again do the same with the x2 tau mix, etc. Right? So that's great. We can apply our existing framework, existing analysis as it is. But note that here we are dropping most of our points, like a big fraction of our points are completely dropped, which is not desirable in practice. And that would also reflect in our convergence rate. That is, our convergence rate will have terms like tau mix by capital T, which is much worse compared to, say, 1 by T rate that we get for IID
You have
setting.
to stick to some simple predictions that actually make sense to, I guess in some donability context.
So the standard SGD data drop completely drops it, like it doesn't use them at all. But you are pointing to a correct direction, we will want to use them somehow, and that's what this talk will be about. Yeah.
I mean, there's also the question of how.
But the dependencies will still be there, right? Like just shifting cannot help. You need to do something more on top of it. And I'll give you examples of what kind of things we can do. Any other questions, by the way? Feel free to stop any.
The smallest degree.
Okay, great.
I don't know if that's...
All right, and in fact, in general setting, this is the best we know theoretically also. That is, there is this nice paper by John Ducci, Alek Agarwal, and collaborators, where they come up with this algorithm, and what we show is that, unfortunately, this is a lower bound also. That is, in general, for arbitrary Markov chains, even for linear regression problems, your best convergence rate that you can hope for is tau mix by capital T. And actually, this bound is not even dependent on just, say, applying SGD algorithm. This is an information theoretic bound. So you cannot hope to do better than this in general. Right? So this makes us sad, and GPT thankfully has written a poem about it. But it says that we must keep on going, we must push forward. So what do we do? Well, like any sort of theoretician got their solved, we will put some assumptions on the problem and try to make it easy. But we'll try to make sure that the assumptions are reasonable. Right? So one type of assumption that we found which works well is that suppose we put some kind of assume some kind of realizability. That is, suppose we are looking at the linear regression problem. That is, we have some linear model or linear function that we apply to x, which is given by inner product of w and x. The goal is to find w, and the target is to find optimize against this target variable y. So here, suppose we assume that there exists some W star, so that Y is given by inner product of W star, comma X plus epsilon, where epsilon is a Markov, like comes from some Markov chain, let's say, but expected value of epsilon is, let's say, 0. So we are putting this realizability assumption that there is indeed a W star, which is an optimal solution with some noise epsilon, which is 0 mean. So under this situation, we can show that there will be some, like in information theoretically, we are at least safe. That is, there exists some algorithm which will achieve 1 by T rate. Now the question is that can we come up with some streaming SGD style algorithms to achieve this rate? And we also want those algorithms to be practical, like you don't want it to be sort of, so things that we cannot really use in practice. So for this, like, because this problem, as I mentioned earlier, appears very regularly in things like time series analysis and particularly in reinforcement learning. So people have come up with a bunch of techniques to solve them, although they didn't really analyze them very rigorously. But one very sort of practical heuristic that is being used is called experience replay. So the idea is very simple, as it was mentioned. So what we do is we take our data points and divide them into some buffers. These buffers can be overlapping also. And now what we do is, in each buffer, we will process data points in some order. So they don't need, and we don't, so SGD generally will process all the points in forward order. That is, it will first process this point, then this point, then this point, then this point, then this point, and so on. But in our buffer, maybe we are allowed to process data points in different order. So for example, there was this technique called uniform experience replay proposed in 1992, where you take each buffer and you sample points uniformly at random from this buffer and process them. Right? Another idea is, which is actually quite popular in recent past and was also used in these techniques called DQN, which you might know from AlphaGo. So those techniques typically use prioritized experience replay. So there the idea is that we look in the buffer what is the loss value that a data point got, and we will prioritize those data points, right? Unfortunately, like so far, we don't know of any analysis under reasonable settings for these two techniques. And as we'll show you, like, I'll try to show you a little later that actually these techniques might be very unstable and might not give you very good results in general. Recently, like in 2019, Rotino proposed this technique of reverse experience replay. It was sort of a concurrent work, so we also came with this similar technique around the same time, which processes data points in reverse order in a buffer. So you take a buffer, and rather than sampling from the buffer randomly or in some kind of forward order, we are taking the last point, first processing it from our SGD algorithm and going backwards, right? So, like, so this is basically our reverse experience replay method that we use, which is that take each buffer. All the buffers are non-overlapping, and in fact, we have some kind of gap between these buffers. This gap is there to ensure that individual buffers are independent of each other. So if we have a gap of, let's say, tau mix, then because of mixing time gap, these buffers at least will be independent of each other. Within buffer, there are obviously dependencies that we'll need to worry about, right? And within a buffer, now we are going in reverse order.
Sticking around.
So that's it. Like that's a simple idea that we would want to use and try to show that this algorithm really works in theory also.
Algebra for distance matrices, and this is
okay, so let's look at a very precise problem and see how this algorithm will work. So let's consider the problem of learning linear dynamical systems. So what the problem is that like this can be thought of as a standard autoregressive model or VAR model used in time series analysis. That is, we have some data point xt. We generate next data point xt plus 1 by applying a linear transformation A star to it, plus some zero mean noise.
So I'll
right?
talk about that.
And the goal is, given this single trajectory of x1, x2, so on, estimate A star.
I really like.
This you can write as this simple optimization problem, that is, given xt plus 1 and xt, you want to find an A that minimizes the L2 norm square distance between them. And this we can write like in its empirical version like this, empirical risk minimization version like this. Now, if you apply stochastic gradient descent, the stochastic gradient descent will have this gradient term, and clearly because at minus 1 is dependent on xt,
what is the
and
distance
xt is dependent on xt plus
So we're
1,
given a dataset
or other way around,
of
xt plus 1 is
endpoints in
dependent
two
on xt. Because of that,
we have a
you cannot
distance
really
function
apply,
like
you
L1,
can apply stochastic
L2,
gradient descent, but it will have some
L2
bias,
descent.
and it might not converge to the
And
optimal
these
solution.
points sort of implicitly define
How does
an
SGD
inviolate
RER
function
works
for
here?
each
The idea is very
ij entry is sort
simple.
of the
As I mentioned, you take one
xi
buffer,
exchange.
process
So these
the
are very
last point in the buffer.
nice
That
and,
is,
you know,
I will
standard
take
objects.
xb minus 1 comma xb
And they're
pair, which
quite
is the
natural.
last
They show
point,
up in many
and I'll
cases,
apply gradient to
especially
it
in
for my first
like they represent,
iterate
like,
A0.
some similarity
Then for my
matrix,
next iterate
matrix,
A1,
and they're used
I will
for
take the next point in
filtering
the
and so
buffer,
on,
which is
lots
xb
of
minus
other
1, xb
applications.
minus 2, and
But they're
again
kind of
apply this
expensive to
gradient
store and
descent,
use, right?
and so on.
If you actually
Once this
want to
buffer
complete this
finishes,
distance matrix,
I will leave the
that's
next
already
Taumix
expert time
samples
and space.
completely,
And
and I will
expert is
start
quite slow
processing
if you
the
know,
buffer,
n is even a
the second buffer from
amount, like
here.
if you ever coded something,
One by
in
one,
Square will
right?
take a long time to complete.
So this is the
So,
simple
yeah,
algorithm.
The motivating
And
question is, can we do
what we observe is that the simple algorithm, when
And,
we
the
apply
hope
to
is
this
that,
problem
you
of
know,
learning
if we
linear
know the
dynamic
points,
system, gives
we
us
should be
nearly
able to say
optimal
something
solution,
about the
right?
distance matrix.
So what does this theorem say? This theorem
So,
says that after
one,
t steps, that is after
key
seeing t
point
samples,
that we take in this
we will
work
be
is
able to
sort of,
recover this matrix
to
A
try to
hat,
understand a
which
matrix
is close
vector
to
product
matrix A
of
star
the
in L2
distance
norm
matrix.
sense or
So what
operator
is
norm
a
sense
matrix vector
up
product?
to this much of error.
Matrix
So
vector
this
product
error
takes in a vector,
has this term
and
of
if your
D,
matrix is A,
which is the
outputs A
dimensionality.
times that vector, you know, takes in
Sigma
Y,
square,
and
sigma
outputs
is the variance of this noise epsilon t.
Why are these interesting?
In
So
the
it turns out
denominator,
that
there is
a
a
lot of
smallest
fundamental
eigenvalue
linear
term
algebra,
of the Gramian,
algorithms,
and
only
we have the number of
access the
samples t.
matrix at hand,
So
matrix
this
vector
is
system.
sort of the
So, for
standard
example,
information
if you ever
theoretical
learn about
optimal rate that you
calculate
can
the
hope
top,
for this problem,
eigenvector
right?
of the matrix,
Note that there is
then,
absolutely no dependence
essentially,
on the
you only
mixing
need
time
matrix vector
here.
product to sort
So
of,
this is
compute this top
what you would
eigenvector and
hope
eigenvalue,
for
and so
from
on.
like, the sort of
And
the
for many,
optimal
many
rate that
other
you would hope
applications,
for.
like I just mentioned, power
And we can
methods,
extend
linear
it,
systems, and
this
other
technique to
iterative
nonlinear
methods.
dynamical system,
Turns out
etc.
that you can really understand some interesting structures about your matrix at hand by only sort of accessing it through matrix
Yes.
vector products.
Yeah. So sorry,
have a
I should have
matrix
mentioned this. So
vector
here we are
product,
assuming
for
that the
example,
mixing time
for
is,
our distance matrices,
let's say it's a
then we
constant or something like
automatically
that.
get many fast downstream
But yeah, we will,
so it's
like the
only few.
number of samples that we'll be leaving out will be constant factor because
Yeah, and,
our buffer size is of that of tau mix.
Any questions that
So we'll be leaving
Okay,
constant
so-
factor this thing.
so one
So
nice
in some sense,
example
tau mix
that I
can
really
depend
like
on
in
t
this
and
paper
still the rate will be the same.
is,
It's just that
for
our
the
buffer
case
size
that
will
our
become
distance
larger
function
and
is
larger,
the
which ideally we don't
L1
want. But
distance.
yeah. Any other
Turns
questions
out
about the
that
result?
we can actually compute a matrix vector product exactly without ever creating the distance matrix.
Yeah.
So in particular, we can, given any y, we can compute a times y, where a is our L1 distance.
We don't know how to analyze that
In
because there are so
roughly
many
linear
dependencies
time, or actually
that
linear
it
time,
becomes very
with
hard
roughly linear
to provide this sort of
preprocessing that only
optimal
has to be done
analysis
once.
there.
It's kind
And
of surprising.
we do have some
surprising
empirical
result, but the
evidence
answer
that
is
does
very,
not
very
work as
simple.
well. Like there we can show that
And
it
I'll
converges,
briefly
it does
mention
reduce
that
like
these
the
techniques,
error,
at least for
but
this
it
exact matrix vector
plateaus
product, I'll
out
show you
before the error achieved by this
actually
method.
applies to other types of functions, not necessarily metrics, but I won't get into any more detail than that. So, I just told you, right, like for the
But so you're
L1
saying that take
distance function, which is like a
one
very
buffer
natural
and
and common
completely
distance
process it, or
function. You can actually compute a matrix vector product exactly in almost linear time.
yeah, let me show the picture.
So,
again.
the natural question that we ask is,
Yeah.
do all natural distance functions, do they admit fast matrix vector products? And it turns out the answer is no, and there's no in a very interesting way. So for the L infinity distance function, where the L infinity distance is you take your
So you want to
points and
take
just
all these points
look at
as
the
one
maximum
instance,
absolute
right?
value of the coordinates.
Oh, all the green
Turns out
points as
that
one
we can
instance.
actually prove a conditional hardness result that essentially any algorithm
Okay.
that computes a matrix vector product must take almost
So,
quarterly time.
so,
So what does
so,
that
so
mean?
that
means,
is
like,
what we call
essentially the
this
best
parallel
we can do
SGD
is
kind
like
of
a
method.
brute force algorithm
The
where
issue
we
is
kind of
that
create this entire
that
distance
method would
matrix
not be
taking n squared time.
streaming, right? Because you will need to
And,
keep
like,
everything in
multiply
the buffer.
factor in the standard.
Whereas here our buffer size
Right?
scales
And
only linearly with the
Yeah,
mixing time.
like I said, this is a conditional hardness result, and
Any other questions? Yeah.
it's based on this so-called exponential time, strong exponential time hypothesis that I can get into later. But
Yeah.
the interesting thing is that it shows like a separation between L1 and L infinity, right? Like for
That's the
L1, we have
problem
this
with having
fast
these
exact algorithm,
animations,
and for
yeah.
L infinity, we can provably show
Why isn't sigma
nothing
the
fast
same
can
as
be done.
sigma square?
And for some
Sigma min?
mysterious reasons, like, that I don't understand, like these types of separations.
The expectation is over, like, whatever is the randomness in the, like,
for nearest
in
neighbor
epsilon
search,
t.
it turns out that, we have fast L1 algorithms for
So
elements
this
of
G has factor of A star also, right? Because you have A star into X plus epsilon, right?
And
So
lastly,
when
like
you
the third
take
gem
this
approach
expectation,
that
you will have
describe is sort of,
A
let's say
into
that
the
the
expected
problem at
value
hand
into
is
A
to
star,
compute a
sorry,
distance
A star
function.
into this
Say
thing
for the
plus
L2
sigma
distance
square
function, I ask
identity.
you,
So
what is
it
the
has a
fastest way
component of A
for you
star
to
also.
compute an approximate distance matrix. So this already takes n squared time, right? Because there's n squared coordinates. But the interesting thing is like, okay,
It is larger than sigma square. Yeah,
the
yeah.
naive way, if we're in d dimensions, right, it takes n squared d time because we have d coordinates for every n
Yeah.
to compute
It's
over.
better bound.
So if you know some standard,
Like
some
basically, we want to say that if
standard
sigma
rules,
goes to 0, like we
then
want
the
ideally want
first
this problem to be better.
idea that you'll have is to use this.
There is one more sort of minor thing which
And
we are
all it
ignoring
says
right
is you
now,
can take
which
your
is that
vectors
this
in
analysis
and sort of
works
map it down to
under
log n
this
dimensions
assumption that
to
operator norm of
preserve
A
all
star
the
is strictly less
distances
than 1.
approximately.
This
you
nice
use
work
this
by
GL lemma,
Simchovis
and
showed
actually
that at
putting
least
a
for
decision
offline
of
problem,
the actual
that is when you are not doing
one
this
of the
stochastic
most
gradient descent,
common
when you
uses of
have
the
all the points
GL
within
lemma
this
in
thing,
practice.
you can actually get rid of
It
this
takes roughly n squared log n
assumption
time
also.
because,
Like,
we
so
have
your
log n
operator norm
coordinates now,
actually might
n
be
squared
larger than
n
1,
squared log n.
but under
But it
some kind of
turns out that,
spectral radius
in-
assumption, you are
it's
able
kind
to
of a
make it work.
silly result,
We are also able to
but it
do
turns
that,
out
but
that,
not entirely. Like there
all
are
you care
some
about is
more
giving a
assumptions that
distance
we will
matrix.
need there, but I will
An
skip that part.
approximate
That's not
distance
central to
matrix,
this
meaning,
talk.
Say we want 1%
Let's see
relative
how we
error
are
in
doing
all
on
the n
time.
entries.
Yeah, have
You
17
can
minutes.
actually do much
Okay.
better than the GL
So
lemma. Instead
another
of
sort
n
of
squared
application
log n
of the
bound,
same
you get
idea
sort
that we
of n
applied
squared
was
log
to
log n bound. It's
to
not,
that of Q
impressive,
learning with reinforce
result,
with
but it is
this
philosophically
reverse experience replay. So Q
interesting
learning is a
because
very
it says
popular
that,
technique in reinforcement
we can
learning,
get
as I
this,
mentioned
like,
earlier.
really
This
powerful
DQN
hammer
technique, which
if
was
the only thing you
central
care about is
to
sort of
AlphaGo
creating an
for
approximate
beating
distance
this like
And the
world-class
nice thing is
player
that,
on Go.
or the another
Like
interesting
the
thing
Q
is
learning
that
and the
this
DQN
log n
technique
in the
was
GL
central
lemma
to
is
it,
strict. Like, you can't
and
go-
it
you can't make
used
your
actually
vector
both these
smaller.
components that I
But
mentioned here, that
somehow,
is that of
because
online
of
target learning and
some
experience
extra
replay.
structure and because
Right.
you're computing
So here what
many
we did
distances,
was
you
we
can sort of,
took these techniques,
save
we modified reverse
some
experience
places
replay with
and
our reverse
actually
experience
meet
replay,
this
and we were
GL
able to show that now the resulting algorithm does
so,
provably
for the
converge
rest
to
of
the
the talk,
optimal
I'll sort of
solution. And in
give,
particular,
like, most
one
of the
interesting
proof,
thing that we were
all
able
of
to
these
show was that for linear MDPs,
they're quite simple,
this
but
reverse experience
constructed.
replay for Q learning
And,
converges
yeah,
to the optimal
anyone have any
solution, that is to the
questions
optimal
before I
policy, which is first such result. In fact, before this, before this modification, people had shown that the standard Q learning diverges for linear MDPs. So
thing I'll
here
show
we
is
were able to
actually
show
how to,
that by
like,
applying
do
this
this
reverse
thing.
experience replay, we were
It's
actually able to make
like
this
a couple of lines
policy
long,
converge to the optimal
so
solution.
it's not like a very complicated
So
algorithm, but I think it
before
sort
going
of
into
shows the power of asking the
the
right
detail
question.
of this, let me first describe the linear MDP
so
setting
I'll show you how
itself.
to compute this
So
matrix vector
in linear
product
MDP, what happens is that we have some
exactly
state action
without ever
pair.
creating
The number of state action pairs might be infinite now,
So for
but we have some
simplicity,
kind of
let's
feature
consider the
vector
case that
describing the state
this
comma
y
action
vector
pair.
is the all-ones vector.
That is, let's say in your board game example, you have
what is the
some
first
state of the
entry
board
of
game and the
x,
action
y,
that you
right?
take, and you can
Imagine
actually
in our head
represent the
what
state
that
comma
shows
action
like.
pair there with
Well,
some feature
basically,
vector.
it
Furthermore,
measures
the
the sum of the
transition
distances,
probability, that
right?
is
From the
when
first
you
point, x1,
go from
to all
some
the other,
state after applying some action
Right,
to
so
some
the
next state,
first
that
entry of
transition probability can also be written
That
as
means
a
it's
linear
expanded,
function,
right? Like,
and
what
your
is the,
reward can also be
one
written
distance?
as a linear function.
the sum
So
of absolute
AMDP is
values
a
over
fairly
all
popular
coordinates.
way
That's
to
the second line.
model,
Now let me just
like,
switch the order of
this is state action space, especially when the
turns
state
out
action
that
space is really large.
to get this fast matrix vector.
Now, in general,
can
like,
compute this- we can do
one
simple
sort of,
processing
popular way
to
of
increase
solving these
interactions fast.
MDP problems
What is the
is
preprocessing
via
that we do?
Bellman equation. That is,
It's
Bellman,
quite
like this popular
simple,
Bellman
very nice,
equation
which is
shows that
we
the
get
Q
our set of
function, which is
endpoints,
basically
we
the
sort of
maximum
sort
expected
the
reward
coordinates,
when you are in some
we,
state comma action
store
pair,
all these points at every
satisfies this
coordinate in
equation,
every one of
which
these
naturally
coordinates.
gives rise to this thing
that's what
called
gives you log,
Bellman iteration, which
that's roughly,
basically says that given
ND
some
log n
current
times, we have
policy
three
QT,
dimensions, and we have,
so policy you can think of as given
Turns out
state,
that
I have
along
some
each
policy
coordinate,
of
you can-
what actions
once
I
you
will take
store,
in
you
each
can
state.
sort of compute
So
this
given that
prefix sum.
policy,
And that's exactly
I
what
will do this
shows up in this
maximization
sum,
to get
are
QT
these
plus
prefix
1.
sums
And this
on
maximization in the case of finite state action pair you can do
that's
through
all
some
I'll say.
standard
And
dynamic
actually, you
programming,
can-
right?
this
Now,
same
in the case of
centralized
linear
of
functions,
Ys,
what you can show
like a
is
very
that these
clean
Q
idea of
functions
sorting out.
or this optimal sort of reward
I'll let you
can
think
be
about it.
parameterized
But yeah, so this
by
is the
this linear function. That
main
is,
idea behind this.
suppose we have some linear function right now, which defines our current policy. Then for every such policy or such linear function, we will have an optimal solution. That is, there will be some u so that this thing is maximized. Which essentially means that now my Q iteration reduces to finding a W so that this equation sort of have a fixed point. And that essentially means that for a given WT, I will just solve this supervised learning problem and I will just keep on iterating. That is, I first solve the supervised learning problem, update my W, again solve the next supervised learning problem.
So the hard problem that
So this is essentially the algorithm that you'll get, that is starting from some policy which is represented by W0. You will solve this Bellman iteration. And now, because this Bellman iteration is a linear regression problem, we can use our stochastic gradient descent with reverse experience replay, and we will repeat until convergence. And as I mentioned earlier, prior work sort of analyzed Q-learning only for tabular setting. In linear MDPs, this simple, at least Q-learning method was known to diverge. But now with this SGD-RER, we can say that this will actually converge to the optimal solution. I will not go in the exact detail of this result, but what we can show is that Q hat, that is the policy that we obtain, will approximate the optimal policy up to this error of 1 by n. Note that there is no dependence on, again, the mixing time here. So this is again independent of the mixing time. Okay.
Second step is I'll apply
All right.
F.
So again, ChatGPT was very happy with our progress. So it wrote this nice poem. And it is saying that, okay, let's embrace reverse experience replay with open hearts. So we thought that, okay, let's apply it in practice. And we were very sort of, bullish. We directly applied this technique to some standard,
mapping.
Reinforcement learning domains. And what we observed was that the method was failing miserably. In general, it was not doing well at all. And we realized that the reason for that is that this mechanism of just taking each buffer and basically pivoting around it does not work. We need to do a little bit more, we need to be more careful. So the new idea that I did not come up with, but my collaborators Dheeraj and Ramnath came up with, was to pivot according to the loss function in the buffer. That is, you look at your data points, you find out a batch where the loss function is the highest, and you basically set that batch as your buffer that you process. So this is how you sort of set your pivots. And after that, you within each buffer, you are again applying reverse experience replay. And this technique magically works pretty well. So here, I'm showing 4 domains in which, this Q-learning with RER was applied. This is an off-policy setting. And here, this RER++, which is this pivoting plus reverse experience replay, is represented by this green bar. One means that the algorithm is doing well. One is basically, it means that the relative reward of the policy or the algorithm is highest. And 0 means that the relative reward of the method is absolutely minimum. And what we observe is that this reverse experience replay ++ method performs nearly the best in each of these domains. Here I am showing only 4 domains. Dheeraj and Ramnath did these experiments in 10, 12 domains. And we observe similar thing in each of the domains. Whereas there was a bunch of other methods like, this uniform experience replay and prioritized experience replay, hierarchical experience replay, and even this reverse experience replay. All these techniques, in some domain they will work well, but in some other domain they will give completely garbage results. So this technique, the advantage is that it works stably and performs well across all the environments. Yeah.
And what is the sum of all the entries in a matrix? Is this that matrix times the all ones vector, right?
Yeah, so as I mentioned that one, for that environment, one essentially means that this policy achieves, out of all these policies or out of all these algorithms, achieves the highest accuracy or highest reward, sorry.
That readily, implies our...
Oh, that's because...
so before I
that's a silly reason. Basically, I was not able to show this UER of value, which had value 0. So I added value of 0.01 to everything. This was just a hack.
So I have some data sets,
Yeah.
and it doesn't matter what.
So
the
this
data
was
set,
basically due to my
and it's
limited
gonna
Excel
base, right?
skills, nothing else.
So n squared is like a huge number. It's n to the 12.
Any other
And, like,
question
no
about this?
reasonable
So yeah, like as I was saying that by
computation
applying this
like
like, sort of slight modification of reverse
like a very
experience
hard
replay,
thing to
this
store.
technique works pretty well, and like
Like a personal
at least
laptop
in like this
can't store
off policy
this matrix for this
reinforcement
because
learning with the DQN
it's
thing,
not gonna
it seems to
you
be
won't
doing
have
pretty
any
well.
fast
So we are
memory for
quite
that,
excited
even though
about
the data
it.
set is only like 0.3 megabytes,
Yeah.
so you can easily even store it in your phone. And so I'll show you some experimental results on evaluating our matrix vector.
So again, like we are not keeping the entire like
I want
buffer, but we are going to slightly larger
I'll
buffer
compare
size.
To this
So
naive algorithm that
like
actually
2 or
either
3x
computes
the
this
buffer size we
matrix, and then
and
fast
there is another
algorithm
experiment that these folks have, which show that does not
Or if
slow
the
you down a
matrix is
lot.
too
That
big,
is,
like in this last
the
one,
algorithm is still
it
practical,
reduces
the
matrix
training
vector
time or
by.
etc. does not increase
And
too much.
the interesting thing is that for this large data set, like of course the naive algorithm is like
They are not correlated. So that's what I will come to in next few minutes.
It takes like many days
Yeah,
to
I
even
have
compute
7
this
minutes,
on
so
my
I can
computer,
try
but
to
this
explain what's
fast
happening
our
here.
algorithm, it
So
takes
let's just set up the notation. Let's take the linear dynamical system as the running example, right?
Okay,
So
now
so first, let's understand why standard stochastic gradient descent in
Now
the
let's
independent
sort of
setting
give a
works.
high-level
So the independent
idea
setting
about
is where, let's say, I am sampling
this
xt and
problem is
yt,
it's
and let's say
not-
yt
it's
is
not something you
realizable. That is,
probably
yt
wanna
is
do
given by
in
inner product of w star with
create
xt
distance
plus
matrix.
some noise.
But
Right?
it is
So here,
philosophically
when you write down the stochastic
yeah,
gradient
I
descent,
can
like one step of
yeah.
stochastic gradient descent, this is how it looks. That is,
Yeah.
wt plus 1 minus
Problem
w
is the
star, you can
following.
write like
I
this.
want to
right?
create an
And if you expand it by using the fact that yt is realizable,
the standard way like this is
what we observe is that wt plus 1 minus w star
there's a way to get
is
sort of n squared log
is this matrix I minus eta xt xt transpose times the previous iterate plus
So
some
if
noise,
you've ever worked
right?
on sort of these
And you can again explain wt minus expand wt minus w star in terms of wt minus 1 minus w star, that is in terms of previous updates. And what you observe is like
let's say,
this sort of
my
unrolling
data
of the
set is,
equation.
set
So
up
here you can
like-
observe that
then I can make a
like if you look at the
data structure on these
expectation,
points as follows.
this term is completely independent
First,
of
I have
epsilon
this
t
giant
minus
box that
1,
includes all
and
the
similarly
points,
epsilon
and I
t is
sort of
independent of xt.
split
So
my
in
space
expectation, this
into
quantity is
defining
0,
two dimensions
and
by
we are decreasing
regions.
error, right?
And you can imagine how this works in any dimension.
And so this is a
then I-
geometrically
as long as,
decaying
the
term.
points are-
Again, because all the
there's-
data points xt's
as
are
long as points are
independent,
not separated, I can
what
do
essentially you get is I
that
minus eta
results in some
times
trick.
expectation of this quantity, which
But
is some
one way to
sigma.
view
So
this
as long
quantity
as
is
your
actually sort of a
covariance
binary
matrix sigma
representation
is
of all points.
strictly positive
Where
definite,
if I follow the
you
tree,
will have some kind of
it actually
decrease, right?
gives me sort of the bit
In
expansion
expectation.
of all
So
my
that
points.
says that you will
That makes
converge,
sense, right? Like
your
I'm going
expected
left to
value of
right
w
in,
will
x
converge to w
direction or
star
y direction, so that
eventually.
gives me one more bit.
This is not correct proof, or like this is
can
not a
actually use
proof
the
because
property,
convergence of the
filter
mean of your iterate does not mean
of
that
all
your
the points
iterate
in your
themselves
data
will converge, but that you can work out. I will not go in detail, but
And
basically for
actually,
that what you
if
need
I
to do
work
is
on sort of
take
how
the
to use these
error in the iterates and
compressed
write its
representations to
covariance,
allow for
and we will be able to
accurate
show that the
computation.
covariance itself is bounded.
And the goal of this
But
work is sort of
I will ignore
not
that
just get
for now.
accurate computations, but also get
But
fast-
now,
fast
when you apply, say, stochastic gradient descent to the
Right,
same
so,
thing,
so let me
right?
explain at a very, very high
If you
level.
remember, like, we had this term
So
earlier,
first
right? Like,
we
this is
make
the key term
quantity like I've described.
that comes up.
And let's say we want to
If you apply SGD to this dependent
from point
data,
X to all the other points.
then
what we do, we
this
start at
expectation
sort of the
doesn't go
root
to
of the-
zero,
of
right?
this tree,
And
we-
that's
we
the
do a
problem.
DFS search.
That this, because
And
of
every
which
time we
SGD
go
is
down
biased,
the tree,
we cannot apply it,
we can
right?
sort of,
However, if you think
update
about
the
it,
representation
reverse experience replay is
of
precisely
the
solving
cell
this
that
problem.
we're
That is,
interested in, because the
if you look
quantity-
at the
like I
update that is
said,
given by the
it's
reverse
a
experience
binary
replay, it
representation
has
of all
terms
points.
of the form where
Every
x
time we go
b
up,
minus t is
can sort of
multiplied with
delete some bits.
epsilon of b
And
minus
every
t
time
plus
we go
1.
down, we,
So here, like,
we can,
here
add some
xt
bits
was
to the
multiplying with epsilon t minus 1. That is, previous iterates
nice idea is
error
that,
was, or like, noise in the previous iterate
are
was
actually,
getting
like,
multiplied
you
with
actually
xt,
need to
and
keep
this
track of very
is
few
not
bits
zero
as
mean.
you go up and down
But
the
here
tree
the
to,
opposite thing happens.
to
That is,
compute
x
the
by
distances,
x b minus t is multiplied with
accurately.
epsilon b minus t plus 1.
And particularly in this,
right?
like, sort of
That is, the noise in the
normally
next
you would need
iterate is multiplied, or
previously you
next
might have
point
needed to
is multiplying with
keep
my
track of
current
log n
point's
words, right, 'cause it was log n
covariance.
dimensions,
And because of
GL.
that, this
But here
expectation
actually
term
it turns out
completely
you
goes
only
to
need
0,
one word,
and
roughly one
we can
word,
show that will
you only need to
converge.
keep one word of
Like it is in expectation, it shows that expected
the
value of
idea is
wt plus
kinda
1 converges
simple,
to w star.
if you wanna
A lot more
compute
work
the
needs to be
distance
done
between
because
x
this is not enough.
some
We will
other
need to
points.
show that the
If they're
covariance
sort of
also
far in
behaves
space,
nicely.
then you
But
don't really need
presently
high
that can be
precision,
shown.
big representation
I'll
of the
just
points,
ignore
right?
all
If you have
this.
very coarse representation,
So let me just
then as
summarize,
give you an accurate answer.
learning with dependent or micro-event data is quite important because reinforcement
And
learning, time
so
series
the question
analysis,
is,
like there are a
how
bunch of
far do we have to
applications
look
here.
before,
In the
things
worst
get,
case, like if you don't make
coarse
any
enough that we
assumption
can
about the
And
Markov
it turns
data,
out that
then even for
roughly
linear
the-
regression problem, we will suffer a mixing time factor,
sort of the
which
view-
can be
the,
quite important,
range
especially
that we have
in
to keep
reinforcement
track of
learning
is like-
problems where
it's a funny
every
number,
sample
but
is
it's
really
it's like
critical.
log n
So
levels.
just
It
wasting
turns
so
out
many
that that's
samples
sort of the right answer.
cannot
Like,
work well
you
in
only have to
practice.
keep track of bits.
However,
there
when
are
the noise has
roughly
some
log
kind
n
of martingale
levels,
increment
with
property,
respect to x.
then
And
we
the
can
rest
show
you can
that the
actually do away.
algorithm, then we can show that at least information theoretically, we can get rid of this
Yeah,
Taumix
and so
factor.
what ends up happening is that
And
after doing
what
this,
we are showing is
DFS
that by
version
using
2,
reverse
you're
experience
getting the
replay with some more sort of,
representation
tricks, we can show that, yeah,
points that you're
this
at.
Taumix factor
And
can be
after some
completely
point,
removed and SGD
after,
works
after
well.
you're in some cell, you
And we could
realize,
show
okay, I don't
this
need to keep
works
track
in
of
linear
bits
dynamical
anymore, and I can
system,
just, like,
non-linear dynamical system, as well as
I
Q
can traverse
learning.
the tree and then
In
maybe
terms
I
of
get to this loop.
future directions, there are a lot of open directions. So first of all, I talked about this RER++ method, which works well in practice, but so far we don't know why, as in we don't really have a formal proof for it. So that's one problem that I feel is very important to understand and figure out what's happening. But then another thing is that most of our work applies to only linear regression, that is least squares problem. So applying this to more general loss functions would also be quite interesting.
We only needed to keep track of.
So thanks a lot for listening, and again, ChatGPT is quite happy
that's
and
the very,
quite
very
excited
high-level
about reverse
idea of,
experience
like,
replay. So
how you can sort of compute this
That's all I have.
matrix faster. And I guess to summarize, it's like we're reusing a lot of computation, right? In particular, we don't have to keep track of the representation beyond this common ancestor, right?
Yeah.
If we're interested in this subtree, because everything else was the same. And also,
it's a good question. Right now, we don't know.
we get too far
So
in
we
the
don't
tree,
know, for example, that rather than
these
using
points are really
Taumix size,
separated,
buffer
so
size,
our bit representation
if you
is
have
very
root
close.
Taumix, then
So
what
by,
happens? Like, will it
I
lead
guess intuitively we're
to
kind of reusing a lot
still
of
like 1 by
computation,
t,
and
or
that's
like
why we can get this improved bound of n square log n.
constant size? We don't know.
Yeah,
At
so
all.
I
So
won't
that's
get
a
into
great
more
question,
details
and
'cause it gets
yeah,
a bit
I'm not sure.
that's like
And
very-
another thing is that, like, this gap thing also is quite annoying. So ideally, we want the buffers to be
I have
like, because in
some
practice people
other
use
instances
overlapping
on the
buffers.
paper, in my opinion.
So can we use overlapping
I have
buffers
some, like,
and
philosophical
still
musings
provide
about
some analysis?
which
That also we
metrics
don't
actually
understand.
admit fast matrix vector products. It's not like a concrete answer, but there's some evidence that this L1 is like a very special metric. And like I said,
So those terms are there. I'm hiding all those. So linear MDT we don't, but we have dependencies on the norm of the parameters. And in the tabular setting also we have the analysis. There we have the standard dependency, that is the state size and action size that will come in the error term.
It doesn't matter what these bounds are, just like
But
one column is smaller than the other.
basically there we are matching whatever is
And the
known,
reason
like
is,
whatever is
like,
the
this
best
is
known
a
there,
black box manner,
we are able to
catch
provide
fast
analysis
matrix
that
vector
matches those optimal
Other people
values.
knew that matrix vector products could be used to compute eigenvalues or low rank approximations
Thank you.
faster, and you can just compose and get interesting results.